Which of the following is an orthonormal basis for the column space of the real matrix given by this? Okay, so, I mean, first thing I want to do is figure out the dimension of the column space here. I don't remember, I'm sure there's techniques given a non-square matrix finding an orthonormal basis for the column space, but you know, I noticed right away that the first two vectors, the first two columns of the matrix are multiples of each other. So, you know, I have 1, -1, 2, -1, 1, -2. These are, the first two columns of this matrix are just negatives of each other. So we can eliminate the second column altogether. Oops. We can eliminate the second column and it won't change the column space. So let's write down the rest of the matrix here and figure out if there are more linear dependencies. So if there were, you know, add the two together and multiply by -1. That doesn't work. Well, hold on. Let's go. How do I figure out if there's another redundancy here? It'll be x plus 2y is equal to -3, and -x minus 3y is equal to 2. If I solve for x and y and it gives me the same relation in the third row, then we're fine. Okay, so let's add these together. This will give -y is equal to -1, so y is equal to 1. So x plus 2 is equal to -3, x equals -5. Okay, so let's just check. -5 plus 2 is -3. 5 minus 2, or sorry, 5 minus 3 is equal to 2. Okay, so now let's check to see if that one holds. X is -5 plus 5, that does equal -5. Okay, so there is another redundancy. What I think I will do here then is I will parameterize the column space. Oh, hold on. This means I need only two of the columns because the third one is a linear combination. Yeah, so it's 1, -1, 2 times t plus 2, -3, 5 times s. So I typically don't like using process of elimination to figure these things out, but there's not going to be a unique answer to this. If I want an orthonormal basis for the set of all vectors, it looks like this. There's not a unique answer because any rotation of that basis within this space will still hold. But I can eliminate some answers right away. So A is eliminated because the third row would always be 0. So you're gone. B is eliminated because it gives a three-dimensional set. And we know that the span is now only two-dimensional. C is also eliminated, again, because the third row is always 0. D is eliminated because these are not, these vectors are not of norm 1, of length 1. And so by process of elimination, the answer is E. So these the vectors for E, which I'll write down here, 1 over root 6, negative 1 over root 6, and 2 over root 6, as well as 1 over root 2, 1 over root 2, and 0. So these vectors are clearly orthogonal. You take a dot product, you clearly get 0. You can check very easily that they both have magnitude of 1, so that's good. I mean, I guess, we would technically need to check that the span of those two vectors is the same as the span of these vectors here. What would the easiest way of doing that be? I suppose if we take the cross product of these two vectors, that'll give us the direction which is not spanned. And if we take the cross product of these two vectors, it gives us the direction that these two vectors do not span. And so the cross product of these two vectors should be parallel to the cross product of these two vectors, at least if this is an orthonormal basis for this thing that we've spanned. But I mean, I'm confident that this will be the correct answer. Again, I typically don't want to resort to process of elimination if I can do it directly. But you kind of have to in this case, because there is no unique orthonormal basis for the span of these two vectors. But you can eliminate the other four options really quickly once you do this. Yeah, so not much more to say about this one, but if I think of anything, I'll put it down in the description. Thanks for watching.